Yeah, so let's create this distance function. Let's call it rho. Uh, it's a function of q. It's defined as the position q minus position at goal. Okay. So this is just the distance from. Uh, hold on, let me fix that. There's no goal. Uh, so let me draw something before I get there. Let's say assume that uh, this is the robot q, and then there is an obstacle here, and let's say that this obstacle um, is at location B. Okay, and clearly what we want to do is we want the robot to, if it's going like this, we don't want it to go and bump into the obstacle. So with that in mind, let's see how to do this. So first we'll define a distance function, and instead of defining the distance with respect to goal like we did previously, we'll define the distance with respect to the point B. So we have P of Q. This is the position of Q in world frame minus, let's say that this is B in frame 0. B in frame 0 would imply that it's the position of point B, or the obstacle, in world frame. That the 0 denotes that. So how do we use this? Well, this is what we'll do. We'll define the repulsive potential as follows. So what we want to do here is effectively this. We want to look at some neighborhood, some, let's say, circular distance. That's the easiest one. And let's say that we choose this to be rho 0. Okay, this is something which the user chooses. So what we want to happen is that if the robot is anyway close to, or let's say it's further away from rho 0, then the obstacle is not going to affect the motion of the robot. So we will not do anything. So we'll say that the attractive field, or the repulsive field is 0. So it's 0 if this rho of q is greater than rho 0. However, when it comes close to the goal, we want this field, that the repulsive field we generate, to repulse the robot. So one way of doing that is to define a function which looks like this. I'm going to put a constant here, eta, divided by 2, 1 divided by rho of q minus 1 divided by rho 0 whole square. And this is when rho of q is less than rho 0. Let's just put less than equal to. Yeah, so let's think what's going on here. Well, when you can see that when rho is the distance from, is this distance. So that rho is this 0 means that there's no attractive field, a repulsive field close away. The moment it hits this point, okay, so what will happen is rho would be equal to rho 0, right? Rho will be equal to rho 0. When rho becomes rho 0, you'll have 1 minus rho 0 divided by 1, sorry, 1 divided by rho 0 minus 1 divided by rho 0. So the field is going to be 0. Right? But then as it comes closer and closer to B, it'll actually start blowing, it starts becoming increasing. So it'll be substantially higher as you get closer and closer to B. When rho becomes 0, so when this goes right at B, okay, so let's say that this rho is now at B, you'll see that this distance is effectively 0. So you'll have 1 divided by 0. So 1 divided by 0 is infinity. So the potential is going to be infinite at B. It's going to be 0 at rho 0. And so it'll increase very quickly. So if the obstacle here, the way we treat the obstacle here is just we're assuming it to be a point obstacle. That is, at B, we don't want it to go at B. And so we want to have a very, very large potential field or repulsive field at B. Now, if this thing had a finite size, like a radius, then you want to adjust rho 0 so that the potential is still very high over that radius. So if let's say that the actual obstacle is something like this. Okay, so the potential is going to be infinity at B, the center, but it will still be finite at this point, right? Because this thing is going to be inside this rho 0. But by ensuring that this rho 0 is big enough, you can ensure that the potential is much, much higher, that will never get to that radius, which I showed with the hatched lines. Okay, so it's just a matter of tuning how you choose. It's just a matter of tuning rho 0 depending on how safe do you think it's to go closer and closer to B. So with that, we can write the force. The repulsive force is basically the negative gradient of du repulsive. The force repulsive will come out to be, of course, 0 if rho q is greater than rho 0, but it will be, and this expression is a little bit complicated because you have to use chain rule eventually. So eta divided by, so eta, so the 2, when you take a derivative, that 2 and this 2 below will get cancelled. Then you always keep this as it is. Then you need to take the derivative of this term, which is by the chain rule. So that will be rho square q. And then you need to take the derivative of this term. So that will be the gradient of, or the Jacobian of rho. And this is all to it. So rho of q is greater than rho 0, and then the rho of q is less than equal to rho 0. So we use one or the other depending on where you are from. Okay, so this term here, so the gradient of the distance actually comes out to be uh, a unit vector in the direction of rho, very similar to what we had got earlier. I think we had a attractive field where we force. So when we took the gradient of u, where u was the norm, that came out to be a unit vector. Similarly, this will be a unit vector, this rho q, because we're taking this magnitude, this rho, and then taking its derivative. So let me make some space for that. Okay, so the gradient of rho is just the unit vector. So it's going to be p of q minus b divided by p of q minus b. This is what we call a unit vector in the direction of the line connecting the point q to b. And this eta is a user chosen quantity. So you can choose whatever you want. The larger it is, the stronger is the field. Okay, so let's put all of this together. We have come up with uh, a vector field for, so this is the key equation we'll be using. So depending on the distance, you can have this force. And for the repulsive field, we have this expression. Okay, so this one which we talked about, you will choose a rho 0, and then that will determine how the force acts or doesn't act. For the attractive field, we would have a different way of doing it. We want to use the quadratic profile, quadratic potential for the closer to the goal, and then we want to use the conic further away, so you have a constant force. So we'll see how to use that. Before that, let me just show you what the repulsive field looks like, and then we'll see how to use this to navigate a car. Okay, so first I have 1D repulsive field. So essentially, it's one dimensional, so it's going to have u on the y-axis and x on the x-axis. I chose the obstacle to be at 5. I chose rho 0 equals 2, eta is 10, and then this is something which is just used so that, what happens is when you go close to bx, you'll have infinite potential, but I can't show infinite, so I'll just going to put cap it at 1. So if you run this, essentially it just does those two conditionals which I wrote down. Okay, so here you can see that it is rho is 2. Okay, so plus or minus, and bx is 5, so 5 is here, so plus or minus 2, so 5 minus 2 is 3, 5 plus 2 is 7, so 3 and 7, you'll see the potential growing, and then it just goes to infinity. So if I not put 1 here, let's say I put 10 here, and then rerun this, you'll see it's clipped at 10. See, it's clipped at 10, so it just goes to infinity, but it starts growing here. So it's a field which will tell the potential to go away from hitting that infinite point, right? But at this point, it will have some non-zero field, but you can see how quickly it grows. So the force sort of resisting it very quickly as it comes closer and closer to that. Now, I also did this thing, which is plotted this on a two-dimensional. Problems we'll be solving will be two-dimensional. Here I have x and y. I just chose it to be at the origin, bx, by, that's the obstacle. I chose rho, the radius to be 1. I clip it at 1. Eta is 10. So then this is just showing you how to create the field. You basically have a conditional. Now I put zeros for u rep, but only if it is in that radius, rho 0, then I use that formula which I wrote down some time back. Okay, so we'll run this. Okay, there are two plots. The first one is a 3D view, and this one is basically the contour plot. So this is like if you took slices at different heights of u and then you project it on the 2D plane, this is what you'll see. So the yellow means it's very high potential. 0 means low potential. Clearly it's 0 most of the places where you don't want the field to act, but closer to, as you hit this radius of, I think, is it 1? I forget. What's the radius? Rho is 1. So once you start hitting a radius of 1, it should start spiking. So plus or minus 1, so it's close to this, starts spiking. So it's a band you cannot see, but spikes quickly. Okay, so this is, as I said again, this max is something I created. I could just make it 10. and then it will show you. Should be similar, I think. It's running. Okay, that's strange. Oh, I did not close this. I see. Now it'll run. Yeah, it's just that here it just, you can see more rings here, and then it peaks at 10 because you get more levels to show when you have that kind of, it'll run again, I think. Yeah.